my name is Han Tran. In this video, we're going to be taking a look at the lever rule. So this video is the final video in a series of videos that talks about Raoult's law. It talks about the bubble pressure, bubble temperature, dew pressure, and dew temperature. And then we also, in this series of videos, have calculated a flash calculation using Radford-Rice method. And we did this in Python, and so we coded out the calculation, and along with coding out the calculation, we also coded out functions for the bubble pressure, bubble temperature, dew pressure, and dew temperature. And so here I have the phase diagrams that we coded out, and we're going to be primarily looking at the phase diagram on the left here. And so it is the pressure versus the mole fractions. And so we plot out these diagrams. What this diagram means, and what these two diagrams both mean, is that this top area here in the top left corner is liquid, and this bottom here area in the bottom right corner is vapor. So in between the two curves here, what we have is we have a vapor-liquid equilibrium, and so anything in between those two curves are going to be vapor and liquid. And so in a previous video, we talked about flash calculations, and basically we talked about how a feed will go into a flash drum and separate out into vapor and liquid, and this vapor and liquid will travel out in two different pipes, and they will each have a mole fraction. So there will be a vapor mole fraction and a liquid mole fraction, and their feed will also have a mole fraction. And so these mole fractions are of a component within the mixture. And so essentially the feed is somewhere in between this curve here. As you can see, it's going to be vapor and liquid. And so at a set temperature, whether that be 223 Kelvin, whatever the set temperature is, the feed is going to have a part that is vapor and a part that is liquid. And so the vapor is going to have a vapor mole fraction per component I, the liquid is going to have a liquid mole fraction per component I, and the feed is also going to have a feed mole fraction per component I. So if we look at mass balance, what goes in must equal what is coming out. And so we have a feed going in, and then we have vapor and liquid coming out. Additionally, the mole fractions are going to be equivalent. So we have the feed times the feed mole fraction of component I going in. We have the vapor times the vapor mole fraction of component I coming out, as well as the liquid times the liquid mole fraction of component I. And so if we take this mass balance equation and plug it in for the feed down here, what we get is the vapor plus the liquid times the feed mole fraction is equal to the vapor times the vapor mole fraction plus the liquid times the liquid mole fraction. And if we distribute out the feed mole fraction, we get the vapor times the feed mole fraction plus the liquid times the feed mole fraction equals the vapor times the vapor mole fraction plus the liquid times the liquid mole fraction. So if we move like terms to the same side, what we get is the liquid mole fraction, or the liquid times the feed mole fraction minus the liquid times the liquid mole fraction equals the vapor times the vapor mole fraction minus the vapor times the feed mole fraction. And if we distribute out like terms, we have the liquid times the quantity of the feed mole fraction minus the liquid mole fraction equals the vapor times the quantity of the liquid mole fraction, the vapor times the quantity of the vapor mole fraction minus the feed mole fraction, all the mole fractions for component I. And then if we move this quantity over this way and the L over this way, we are left with the vapor liquid ratio, so vapor over the liquid, equals the quantity of the feed mole fraction I minus the liquid mole fraction of component I, and over the vapor mole fraction of component I minus the feed mole fraction of component I. So what we have here is we have the lever rule. And so what it's saying is that the ratio of the vapor and the liquid is also the ratio of the differences between the mole fractions. So if we look back up here at our diagram, this side here is the vapor mole fraction minus the feed mole fraction, and this side here is the feed mole fraction minus the liquid mole fraction. So we have the differences on either side, and what this is acting like is it's acting like a lever or a seesaw where they are balancing out. And so that ratio equation down here that we derived is actually the lever rule.